Hey guys, welcome to lecture number, I don't know, 17, I think. Yeah, 17. And well, so far we have finished 3 chapters, and now we will start something new and I would say more interesting, but also more difficult. Well, in this lecture, we will be talking about the extreme values of continuous functions, but don't be mistaken by the title, because this lecture will have some derivatives involved here. So let me, and well, you will see now in this chapter, you will see more qualitative properties of derivatives. This will be much more interesting material than, and I would say this chapter and the next chapter will be the most important 2 chapters of this course. So I would suggest you better pay attention really closely to these 2 chapters. All right. So first, let's talk about absolute maximum and absolute minimum. So these are the 2 definitions that I have in mind. So let's start with the first one. We say that, let's see what an absolute maximum and absolute minimums are. Because here you will see that we will be also, we will see that functions in general, they have some minimum, but that, or maximum, but that minimum or maximum can be also absolute, and we will see what this means, but also can be relative. And we'll also see what that means. All right, so first let's start with the absolute extrema, well, absolute maximum or minimum. And well, we say that a function f has an absolute maximum at, let's say, a point C, right? Which is C is a point given in the domain of the function. If this inequality will happen, if f of C, if the value of f at that point C will be greater or equal than f of x for all x in the domain of f, right? That's absolute maximum, right? So that's what you have to keep in mind. Absolute maximum means this thing here, right? So imagine that f of C will dominate f of x. That's how you're gonna remember this. So we say that in this case, f of C is the absolute maximum, right? So, right, f of C is greater or equal than f of x. And we say that f has an absolute minimum at the point C if, guess what, the other way around. So if the reverse inequality holds true. So if f of C is less or equal than f of x, right? So f of x dominates f of C, right, in other words. And this happens for all values of x in the domain of f. So in this case, we say that f of C is the absolute minimum. So these are the 2 notions that we have to keep in mind, the absolute minimum and the absolute maximum, right? You see them right there, right? So now we would like to see some examples of how do these 2 look like on a graph of a function. And now let's see some examples of graph of functions, right? So just one more second to look at these, so keep that in mind. And now let's look at examples. So I have the following example in mind. Look. You see, look at the graph of this function. In fact, let me look at this. So this is the function. It goes through 1, and it goes up, all the way up to this point, right? So these are the 2 points. So this is the point of coordinates 2, 5. This is the point of coordinates 0, 1. And this is another point of coordinates -1, 2, something like this. Anyway, so You see, the graph of this function also includes these points. Keep that in mind. Look. What can you tell me if you look at the graph of this? Do you see any absolute minimum, which is the lowest point on the graph, or the absolute maximum, which is the highest point on the graph? Do you see them? Well, as you can see, this is the absolute maximum is right here, right? Is this point of coordinates 2, 5, right? And it's right here. But the absolute minimum, you see, it's right here. It's this point of coordinates 0, 1. So this function, the graph of this function, has an absolute max and an absolute min. Now I have a question now for you. Based on your intuition, what would you say? Do you think all functions have absolute min and absolute max? What do you think? Not necessarily, right? So you can find exactly, wow, that's a great observation Travis made. So not if they're on the line, correct? So you see, now let me show you an example which is different than just a line of a function that has an absolute minimum but no absolute maximum. And in fact, I'm gonna take the same function, but I'm gonna modify it a bit. And let me show you how I will modify it. So again, I have the graph of this. So it goes like this. See it here. And here, pay attention, I have a hole, right? So it doesn't, this point is not on the graph, but here it contains this point of coordinates 0, 1. So in this case, if you look at this, and also here I have a hole. If you look at this function, if you look at the graph of this function, you will see that, you see, does it have an absolute minimum? Well, if you look at the graph, yes, it does, right? Because the lowest point on the graph is the point of coordinates 0, 1, which is contained, right? But here I have a hole at this point of coordinates 2, 5, I think, right? And it has no absolute maximum, so because the graph doesn't contain that, but we do have an absolute minimum, right? So this is an example of a function with an absolute minimum and with no absolute maximum. But also we can have the other way around. We can have an example of a function with a absolute maximum, but with no absolute minimum. So we can do the same thing. The only thing now we can modify is just to have a hole at that point 0, 1. So let's do that and look at it. Again, we have the graph of this. So we have a hole here. And here the graph contains these 2 points. And now between them, we have the graph is this guy here, right? It goes all the way to the point of coordinates 2 and 5. So now if you look here, I have a hole. So this means that this guy has no absolute minimum, but it does have an absolute maximum, and it's right here, right? Well, maybe you'll think, well, okay, so I've seen functions which have both absolute minimum and absolute maximum. I've seen functions that have, well, the same function, I just modified it in such a way that it has an absolute maximum but no absolute minimum, but also the other way around with an absolute minimum but no absolute maximum. So I have all the options here. All right. So now let's see, how do we relate these absolute min and absolute max? And let me go back to the definition, because this is important. So how do we relate these two definitions for absolute maximum and absolute minimum to derivatives? So that is the question. So the question that I would like to address here, how is this related to derivatives? That is the question I need to answer, right? And this will be related to what we will call the extreme value theorem. And the extreme value theorem has the following statement. As you know, before we even go and talk about derivatives and stuff, but let me remind you that the extreme value theorem says that if f is continuous on a closed interval AB, then f has both an absolute maximum and absolute minimum. This is very important. It's, well, what we call the Weierstrass theorem. It's bounded and moreover it attains its bounds. In other words, it has an absolute maximum and an absolute minimum. So keep that in mind. So if I have a continuous function on a closed interval AB, then f has both absolute maximum and absolute minimum. This is important. So that's what you need to know about a continuous function defined on a closed interval AB, right? All right. And now let's talk about well, we said that when we talk about minimum or maximum, we don't just talk about absolute minimum or absolute maximum. We also talk about a relative minimum or relative maximum. So let's see what this is about. So, and pay attention here to the definition between, because there is a difference between relative and absolute. All right, so let's see. We say that a function f has a relative maximum at a point C if f of c is greater or equal than f of x. And here comes the difference. For all x which are in an open interval containing the point C. This is the difference, right? Because we said that in the case of the absolute max, right? We said that this happens for all x in the domain, right? Here it happens for all x containing, in an open interval containing that point. So it's just a small neighborhood, not on the entire thing. So you see, it's on a portion, that is the relative min or maximum. It's not on the entire portion, right? And also, the other way around happens if we say that f has a relative minimum at the point C if f of c is greater or equal than f of x for all x in an open interval containing C, right? The same thing. So, right? And now let me go back again to the definition. Look, I want you to distinguish between these two. So you see, again, when we talk about absolute maximum and absolute minimum, the same, and also for when we talk about relative min and relative max, the same thing happens, but in the case of absolute max or min, those two inequalities hold for all x in the domain of f, right? So I want to make this clear for all x in the domain of f. But in the case of relative, let me go back to, this happens only for all x, right, in an open interval containing C. So both of those inequalities happen. All right. So that's the difference between relative max and min and absolute max min, right? And now let's see some examples. Now let's see examples. So we have seen examples of functions which have we've seen examples of graphs of functions with both absolute mean, max, or functions with the with the absolute max but no absolute min, and so on. And now we would like to see for the same thing for relative max and min. So let's see the first example. The first example that I have in mind is this guy right here. I want you to look at it. So let's see. So we have the graph of this function. So you see it goes like this. It goes up all the way here to up to this point of coordinates 0, 2. Then it goes down all the way to the point of coordinates 1, 1, and goes up again. Okay. Let me ask you something. So you see, do you see any absolute max or absolute min? By just looking at infinity, right? Because it goes all the way down here. You'll be like, oh my God, it depends on how it's defined. But usually if it's defined on the real line, it goes all the way from negative infinity to positive infinity. Okay, but do you see some, on this portion, do you see anything relative max? Well, if you look at the relative maximum point, you see this guy right here, right? That's the relative maximum. It's not absolute maximum because I can have another point right here, look, which is, right, is higher on the graph of the function. And also the relative min will be this guy here. Of coordinates 1, 1. It's not the absolute min because I can have another one right here, for example. Right? So we can say that on a certain interval, we can say that the relative max is this guy here, the point of coordinates 0, 2, and the relative min is the point is at 1, 1, right? So we can say that. So that's the difference between them. So let me write it here. So this is relative max. So this is a relative maximum. And this guy here is a relative minimum. Okay. And now we would like to answer finally our question right at the beginning, because we have said we have talked about extreme values of continuous functions, but we would like to see what's the connection between these and derivatives. And now this is where the entire picture will make sense, I hope. And at this point, we know how to relate these. And the connection will be what we will call critical points. So let's see what the critical point is. So if the derivative, if f prime of c, so the derivative, if the derivative of f at the point c is 0, right? So if we have this, or if f prime of c does not exist for c in the domain of f, then we will say that this point of coordinates c f of d, I think it's a mistake here, I'm sorry about that. C f of c is a critical point, right? That's what we call a critical point. So once again, they must obey this. So either the derivative is 0 or the derivative does not exist. And this number c, for which its derivative equals 0, it's what we call a critical number. So please see the difference between critical number and critical point, right? So the critical point will be this guy here, will be a point of coordinates C, f of C, and this guy here, C, is a critical number, right? So this is how we find out what a critical point and a critical, what it is, what a critical point and a critical numbers are. And now we would like to relate this to minimum and maximum, and maybe to relative min and relative max, and this will be related in the following theorem. And I would like you to look at this. So this will be a very important theorem, because this theorem will tell you nothing else on how to find minimum and maximum of a function f. Well, more specifically, I would say relative min and relative max. All right, so if C is a relative maximum or a relative minimum of a function f, then guess what? Then either f prime of C is 0, so either the derivative is 0 at that point, or the derivative does not exist. So this is what happens, these two here, right? So that's the critical number theorem. In other words, if you would like to look for maximum or minimum, well, relative max or relative min, you always have to look for those numbers for which the derivative is 0 or the derivative does not exist. And now we would like to see what is the difference between, because you see here, I mentioned these two words. Ooch. So I mentioned these two words here, relative max and relative min. And now let's see, how will this be related to absolute extrema? So for the absolute extrema, we have the following. So the extreme value theorem, let's see what the extreme value theorem tells us. So the extreme value theorem tells us that that absolute extrema of continuous function on a closed interval exists, right? So we know that. The critical number theorem tells us that the absolute extrema can only occur, and pay attention, at critical points or at the end points. This is important. I want you to distinguish between these two, right? So the extreme value theorem, again, the extreme value theorem tells us that the absolute extrema of a continuous function on a closed interval exists, which is great. We know that they exist, right? But moreover, the critical number theorem tells us that tells us even more. We know where to find them. So we can only find them at critical points or at the end points, right? So in this case, our function f is defined on a closed interval a, b, and r, right? Right. So in other words, for the critical points, we need to have f prime of c 0, and for the endpoints, we need to evaluate f of a and f of b, right, at the endpoints. So this is how we're going to look for absolute extrema, right? So I want you to look at it again a bit. All right, now let's see some examples. I want to do some examples. And the first example that I have in mind is the following. And now I'd like you to think of it for a bit. So the first one says, if I have this function, f of x is x minus 2 sine of x, I want to find the absolute maximum or absolute minimum of this function. So again, let me write it here. F of x is x minus 2 sine of x. and f is defined on 0, 2 pi, and real value. So that's what we want. Okay, think about it for a bit. So again, look here above. You will see the exact strategy. So what would you, how would you think of this problem? Before we even want to find these absolute max or absolute min of this function, first of all, do we know that these absolute extrema exist? So when I say here, maybe I didn't make myself clear. When I say here absolute extrema, I mean extrema means absolute min and absolute maximum. All right. So what do you think? First of all, we need to make sure that these absolute min and absolute max actually exist. How do we know that? Well, yeah, you can say that too. Yeah, I agree, but well, look above. What does it say? That by the extreme value theorem, what does it say? That if I have a continuous function on a closed interval, we'll get there. First, we need to make sure that this actually exists. Well, do they exist? Yes, because this function here, so f, this guy here is continuous on the closed interval 0, 2 pi, right? So the extreme value theorem tells us explicitly that the absolute extrema of this function exists. All right, we know that they exist. And now how do we find them? How do we find them? By using the critical number theorem, right? Which, if you look, it says that the critical number theorem tells us that these absolute extrema can only occur at the critical points. So basically, we need to take the derivative and set it equal to 0, or at the endpoints, or we need to evaluate the function at the endpoints of the interval 0, 2 pi, which the endpoints are 0 and 2 pi. So let's do that. So first, we need to find critical numbers, right? On 0, 2 pi. So we basically, we compute the derivative. So f prime, if you look here, f prime of x is nothing else than just 1 minus 2 cosine of x, right? Which you'll find it here. You will set this equal to 0, and guess what? Basically, you have this equation. You'll end up with this equation here. Cosine of x is 1/2, right? So what are the solutions of this equation? Well, the solutions are either pi over 3, right? Or you can add 2 pi or 5 pi over 3. So look, these are the solutions. Let's say critical numbers. Right? You just set, you see the critical points or critical numbers, you'll have to look at this. All right, great. And now we will have to evaluate. So we will have to compare values of critical points and endpoints. And let's do that. And we'll have the following chart. So let's see. We have to evaluate. So we have to evaluate f of pi over 3, f of 5 pi over 3, f of 0, and f of 2 pi. And if you look at in this chart, at 0 the function is 0. Okay. At pi over 3 is negative 0.6843, right? At 5 pi over 3 is 6.968, and at 2 pi is 6.28. So let's see which one is the largest, which one is the smallest one. If you look, the smallest is this one here, and the largest is this one here. So the absolute min will be negative 0.68449, and the absolute maximum will be 6.968. And so the absolute, the lowest point on the graph will be this one of coordinates pi over 3, negative 0.6849. And the highest point on the graph will be this guy here, 5 pi over 3, 6.968, right? Okay, is it clear, this problem, this exercise? Like I said, the only thing you need to do is just to, so first, you know that the critical numbers exist because the function is continuous. So you have the, well, the absolute extrema exists. So to find them, you use the critical number theorem, right? And when you use the critical number theorem, you will set up the derivative of f to be equal to 0. And then you find, you solve the equation, you find x, the values of x, those will be the critical numbers. And then you evaluate f of f at those critical numbers, but also at the endpoints, just like we said here. Look, the critical number theorem tells us that these absolute extrema can only occur at critical points or at the endpoints. So keep that in mind. All right, let's see, any questions so far regarding this example? It's pretty standard, I would say. I mean, all right. Let's see another example. If there are no questions, I would like you to think of the following example. So I need to find the absolute max and absolute min for this function. So the function f is given by x to the power 2/3 times 5 minus 2x. And f is defined, so let me write it here. So f is defined on this interval negative 2, 2, and real value. So think about it for a bit. Man, the weather is pretty nasty. Yeah, I saw that. I wanted to go to the office, but then when I saw the rain, I was like, okay, maybe I should stay home. So. So what would you do in this case? So you look at the function, right? Again, the function, let me write it also here. F of x is x to the power 2/3 times 5 minus 2x, right? So this is my function. So what should we do here? Like Sabrina says, we need to find the derivative by the product rule. That's beautiful, right? So we need to find the critical points, right? And basically so that's the first thing we do. So we need to find the critical points on the interval negative, on the closed interval -2 and 2. How would we do that? Oh. You actually hear? Oh my God. Well, let me mute myself for a I hope it doesn't rain with rocks next time. All right, so let's see. We need to compute the derivative. So what's the derivative of f? Yeah, I know. Well, I'm actually, when I'm teaching, I'm close to the window. So my laptop is right here and the window is just right here. So I look, yeah, it's good, but also I get too much light. It's just in front of me, so. So what's the derivative of this function? So again, like Sabrina says, we can use the product rule, right? So let me write it here. F prime of x is what? Is, let's say, x to the power 2/3 prime times 5 minus 2x plus x to the 2/3 times 5 minus 2x prime. And this will be 2/3 x to the 2/3 minus 1, right? Times 5 minus 2x plus x to the 2/3 times -2, right? Which will give us, if we want to look, if we want to, all this mess here, if you look at it, this will give me this guy here. So the derivative of f, so f prime of x is, as you can see, I can multiply them. 2/3 times 5, it will give me 10/3 times x to the power -1/3, because this guy here, right, this baby here, we see it here, this guy is -1/3, so you see it here. And anyway, so you have this, the derivative will be this. And we're going to set this equal to 0. And guess what? Once we set this equal to 0, we are left with these equations. So the equation that we're left with is this guy here. Oops. So it's 10 times 1 minus x, everything over 3 times cube root of x, right? Equals 0. So what are the solutions of this equation? Right? Well, x equals 1. I think it's pretty clear. So the critical numbers on this interval, well, as we want to see them through the equation f prime of x equals 0 is x equals 1. Is this guy here? Great. Now, when x equals 0, let's see, what happens when x equals 0? Well, if you look at the function, the way it's defined, when x equals 0, the derivative, right, because we have this, look at this equation. And we have here on the bottom, we have, so this guy cannot be 0 because it's on the bottom. So when x equals 0, f prime does not exist, right? Great. And so when x equals 0 and x equals 1, these two are both critical numbers. Okay, great. But, okay, they're critical numbers, I agree with that. But which one is which one? So which one do you think is, and in fact, I would like you to tell me, which one do you think is an absolute min or an absolute max? Or are there any other points that we need to evaluate? So what do we need to do at this point? So we need to evaluate, right? So let's write it here. So we need to evaluate f at this critical number. So f at points 0 and 1. Let's write it like this: x equals 0 and x equals 1. So these two are what we call critical numbers. And at the endpoints. Okay, at the endpoints. Ooch. At the endpoints, x equals -2 and x equals 2. All right, so in other words, we need to see who is this guy, f of 0, f of 1, f of -2, and f of 2. So we need to see these 4 numbers. Who are they? Well, you will see that in the following chart, and let me show it to you. And if you look at this chart, and we would like to, and we compare the values of critical points and endpoints. So see, the endpoints are -2 and 2, and the critical points are 0 and 1. And let's see, let's compare the values. So f of -2 is 14.2866. At 0, f of 0 is 0, f of 1 is 3, and f of 2 is 1.5874. So the absolute min is this guy right here. As you can see, it is the lowest, 0. And the absolute max, as you can see, is this guy here. So you see, the funny thing is that the absolute max was obtained at the point x equals -2, which is the lowest. So don't be mistaken. You can be, it doesn't mean if -2 is the lowest, you'll get the minimum. No, when you evaluate f at that point at -2, and you have the greatest value, then that would be the absolute max. Does this make sense? Okay. If it does make sense, let me do another example. I'd like you to look at this one. So again, we want to find the absolute min and absolute max of this function this time. And I'd like you to think of it. So the function is given f of x, let me write it, is the square root of 9 minus x squared. And I would like you to pay attention to this function. And f is defined on the closed interval -1 and 2. And I would like you to pay attention to this function. It's a bit, you need to take something into account first. I was looking here. Diego, I have a question. Weren't you the one that was supposed to go to a wedding? No? Oh, okay, it was somebody else. Because I was like, what the hell are you doing in the class when you have a wedding? Okay, maybe it was somebody else. Okay. So what do you think of this function? First, what do you need to do before you even start talking about critical numbers, about absolute min, absolute max? What is the first thing that you need to take care of? You see how the function is defined is the square root of something. What do we know about the square root? Come on, tell me. What do we know about the square root? And when I say square root, I mean the quantity inside the square root. So what do we know? Come on. So the square root of x exists. Oops. Wait. I think I have to charge my. So the square root of x exists if and only if what? The quantity inside the square root must be what? how is the quantity inside the square root? Can be negative? No, it has to be not negative. So in other words, before we even start talking about the critical points, whatever, critical numbers, before we even evaluate the function at the critical numbers or at its endpoint, we need to make sure that we know precisely what is the domain of the function f, right? So we need to make sure of that. So in other words, let's just wait a bit. Exactly. Maybe you should include those numbers 3. Excellent, right? You would like to include them as well, right? Because the quantity, I say it's non-negative, not strictly positive. All right, so we need first question we need to address, what is the domain of the function f? Okay, so that's the first question we need to address. Great. So in other words, since our function is defined in this way here, so we need to make sure that the quantity inside the square root, so 9 minus x squared is greater or equal than 0, which is equivalent with x squared less or equal than 9, or if you want, equivalent with x in this interval, -3 closed interval. So that's the domain of the function. In other words, well, we need to find the domain of the function, right? Well, okay, let me write here. So first, the domain, find the domain of the function of f, which is -3. So we need to find the critical numbers on that thing, right? So that's what we need to do, right? Okay, great. So we will find the critical numbers of, whoa, what is that? What was that? So we need to find, we find the critical numbers on, actually, yeah, we need to, the domain is -3, the large domain. But here the function, you see, is defined on this interval, -1, closed interval 2. But this guy is a subinterval of -3, which is great. So we need to find on a smaller interval. So since we're restricted to this negative interval, -1, 2, we will find the critical numbers on this interval. So again, we're going to set up the derivative of f to be 0. And the derivative, I'll leave it to you as an exercise, is given by this. So this is an exercise for you. So you will use the chain rule for this function, right? And you're going to set it equal to 0. And for here, this will imply immediately that x is 0. So that will be, and now we will compare values of critical points and endpoints. So the values of the critical numbers are x equals 0. And now let's see. So we need to evaluate f at 0, f at -1, and f at 2. And let's see which one is the largest. So when we evaluate f at -1, we will get that f of -1 is 2.828. When we evaluate f at 0, we will get 3. And when we evaluate f at the point x equals 2, we will get 2.236. Well, if you look here, look at this guy here. This is absolute maximum, right? It's 3 is the largest. And now let's see. Which one is the lowest? Well, 2.8 is greater than 2.2, so this will be the absolute minimum, right, for this function. All right. We see now we restricted ourselves to this domain. And I'd like you to pay attention because I'd like to take the same function now, look, and I would like to do it in this way. So I want you to look at this. And I want you to tell me, in this case, what is the absolute min, what is the absolute max. You see, I don't specify here what the domain is. But we kind of figured it out earlier what the domain is. What is the largest domain for this function? Do you understand the difference? In the previous example, I told you find the absolute max and absolute min of this function on this particular interval. Now I don't specify, but maybe you can tell me which one is the, what is the interval at which this function is defined? Huh? So f is defined on what interval? Can you tell me? We said this earlier. F is defined on con, what is it? -3, 3, closed interval, right? Right, so this is f of x is the square root of 9 minus x squared. Great. Well, so this is my function. So we're going to do the same thing. So this time we'll see, we have to evaluate f of -3 and f of 3. But also, we need to evaluate at the critical points. But we have seen, so the domain again is -3, 3, as we have seen previously. And now we need to find the critical numbers on this interval -3, on the closed interval -3, 3. Right? So again, we'll get by computing the derivative of f, which is that, right? It's 1/2 square root of 9 minus x squared times 9 minus x squared prime, which is -2x, right? By the chain rule, we'll obtain this guy that this is 0, x is 0, right? From this, because this guy is different than 0, it's on the bottom. So the only option we have is that this guy is 0. So x is 0. So when x equals -3 or 3, f prime does not exist. You see the bottom is 0. So I have that 9 minus x squared is 0. So the fraction doesn't exist. All right. So the critical numbers are -3, 0, and 3. And now we would like to evaluate the function at these 3 points. And let's do so. So we need to evaluate f at x equals -3, x equals 0, and x equals 3. In other words, f of -3, f of 0, and f of 3. We would like to see what this is. So let's, we'll have the following chart. I want you to look at it. Wow, we have 2 absolute men. Ooh. So f of evaluated at -3 is 0. So let me write it here. F of 0 is 3, and f of 3 is 0. Wow. You have 2 values here. So you have this here. We also have this. So this 3 is the largest, and this 0, both of them are the low. So we have an absolute max, right? But we also have 2 absolute min. This guy and this guy. Wow. You see, the situation will be a little bit different if we don't restrict our function to a certain interval, right? If we just let it on the entire domain of definition. See, we took the same function, f of x is equals the square root of 9 minus x squared. But you have seen that on if we restrict this to a certain interval, which in our case was negative 2, 1, right? We go back here, something happens, right? We'll get only an absolute man and an absolute max and an absolute min, right? But if we let it go on the entire domain of definition, we will get something different. Oh, see here, we'll get an absolute max and 2 absolute mins. Well, in fact, and the absolute min are obtained at the points negative 3 and 3. All right, okay. And now in the remaining time, I'd like to show you a problem, and probably I will do more examples next time. But definitely you will have these kind of problems at the final exam, optimization problem. All right, I would like you to look at this the statement of this problem. So it says the following: a box with a square base is constructed such that the length of one side of the base plus the height is 10 inches. Okay, as you can see in the picture, you have the base that is denoted by B, and the height is denoted by H. So given that, we're wondering what is the largest possible volume of such a box. So you see, I'm wondering what the volume is. So the volume of the box. So what is the volume of the box? So let's write it here. Do we know a formula for the volume of the box? Do we? Exactly. So the volume will be, in our case, will be B times H, which is B squared times H. But what do we know? So the base squared times the height. But what do we know? So we know that the length of one side, we have this information of the base, plus the height is 10 inches. So what do we know? B plus H is what? So it's 10 exactly. So we know that, or let's say it's given that B plus H is 10. Okay. So I have this equation here. But also I have to find the largest possible volume, and pay attention here. This is the largest. So I need to maximize that function. All right, great. So let's write it here a bit. So as you can see, we have this. So this guy here, if you look, let me write it in red. If you know that that H from here is 10 minus B. So let's plug this one here and here. So we will get that the volume, let's say V, and this will be a function of B, let's say. V of B is B squared times, and H is 10 minus B. We have this formula for the volume, which you will get it here as well. And now guess what? Since this is a function of B, and we would like to find the largest possible volume, we will take the derivative of this, right? So first of all, we need to find the critical numbers. So V prime of B, let me write with a different color. I don't want to make it all red here. V prime of B is what? Can you tell me? Is 10, so it's 20b minus 3b squared. And we will like to find the critical numbers, so we will set this equal to 0, so that's what we're going to do. And once we do this, we'll get these two solutions. So we will obtain either b is 0 or b will be 20 over 3, right? And now we would like to see, we would like to evaluate v. Now we'd like to see which one is the largest, right? Well, b will be 0, right? So v of 0 is 0, it's quite clear. But v of 20 over 3 will be 4,000 over 27, which is approximately 148.1 inches cubed. So that would be the largest volume of such a box. You see, you can use critical points and critical numbers and critical point theorem just to solve an optimization problem. So that's a real world application, right? And of course, there are plenty of questions like this. I can tell you even more practical applications. I can have a fence, and I need to know what is the largest amount of fence that I need to build around my house if something is given, and so on. Anyway, you will see plenty of applications of this type. Any questions about this problem? Any questions? So like I said, the only thing you need to know is just to write a volume formula and to see it as a function of the base, or you can write it, you could have written it as a function of the height if you want. It doesn't really matter, but yeah, that's how you can solve it. And then you look for the critical numbers and so on. All right. I think I will stop here with today's lecture. Well, I have office hours in like 12 minutes. If you have any questions regarding the exam, I'll fix that thing with the last problem. I'll draw the triangle so that you guys can see which one, which angle is theta. But if you have any other questions, please feel free to stop by. All right, so good luck with the exam, and I'll see you on Wednesday. Take care, bye-bye.